Okay, sorry I wasn't in class today. I was sick and wasn't really feeling like I should be at school today. So I should be back on Friday for the review day. And I just want to finish up the last information about human impacts. When we left off on Wednesday, we were talking about mining and the EPA and how people call to disband the EPA constantly because it supposedly costs jobs. And I had gone through the fact that it seems like as coal employment is going down, coal production is actually going up. And I left you with the question of how can you provide more coal with fewer coal miners? And the reason is that in the late 70s, coal mining shifted from shaft mining, where you would dig a shaft into a mountainside, send coal miners down into the shaft. They would mine the ore, they would send it out, and in like little railroad cars, and it was very labor intensive and very dangerous. And coal mining companies shifted to mountaintop removal as the preferred method of coal mining, especially in Appalachia, where you can basically just dynamite the top of a mountain off. And when you have dynamited the top of the mountain off, it exposes the coal seam, and then you can just come in there with large equipment and scoop up the coal, and it is way less labor intensive and way safer than shaft mining. As a result, you need fewer coal miners to get the same amount of coal out of the ground. The other thing that has happened is that you see this decline in coal production. That probably is correlated with the decline in coal demand because as more and more coal fired electrical plants go offline because of age, they're being replaced by natural gas plants. And natural gas is much cheaper and cleaner to burn, and so coal demand is going down over time as well. So this disconnect between mining employment and coal production is way more probably responsible for loss of coal jobs than anything that the EPA happens to be doing from year to year. So the last topic that we want to talk about is human impacts on evolution, and two areas I want to talk about here is antibiotic resistance evolving in bacteria, and then human beings altering selection regimes in natural populations. When we think about antibiotic resistance in bacteria, a good example of this is the Harvard megaplate experiment. This is an experiment. If you just type in Harvard megaplate into your browser, it will take you to a 2-minute video that's very informative. It shows what happens to populations of bacteria as you slowly increase the amount of antibiotic in the agar that they're growing on. And what happens is they evolve resistance very, very quickly. And this is a problem because bacteria, when we're infected with bacteria, the easiest way to get rid of them is to take an antibiotic. And over time, we have utilized antibiotics. And in the process of utilizing these antibiotics, we have made a number of them resistant to these antibiotics. And so here are some urgent threats according to the CDC because of um, because of antibiotic resistance. You'll see methicillin-resistant Staph aureus is here in the list of serious threats. That's a pretty common form of Staph aureus, and any of these things have the potential to kill you. And there are no antibiotics that we have to work against these things. My younger sister actually died in her 30s after being infected with Staphylococcus aureus. And so this can be a serious health impact. Unfortunately, plenty of people die as a result of these antibiotic resistant bacteria. And unfortunately, since COVID, because we shifted during the COVID pandemic to keeping track of COVID, most health departments have done less of a good job of keeping track of causes of death due to things like antibiotic-resistant bacteria. And so we haven't had as good reporting in the last couple of years. And that's unfortunate because that's one of the things that the CDC and the Department of Health and Human Services should be tracking. And so hopefully we'll get back to better surveillance on these types of things in the future. And then the last thing I want to talk about is Darwin's finches. We've talked about Darwin's finches a number of times over the course of the semester. Darwin's finches live in the Galapagos Islands, and tourists go to the Galapagos Islands because Darwin went to the Galapagos Islands, basically. And they typically arrive in Academy Bay, which is on the main island where people arrive. And residents have put up bird feeders to attract the birds for the tourists because the tourists come there and they want to see Darwin's finches because Darwin's finches are famous. So the supplemental feed presumably has the potential to reduce competition for food that traditionally drove beak morphology apart through the process of disruptive selection. So I just want to show you a few slides to drive this point home. Here we have Geospiza fortis. There's a small beaked version of Geospiza fortis on the left and a large beaked version. These are the same species, just different beak variants because these birds are undergoing disruptive selection. And so what these researchers did was they published this in 2006. They went back and looked at historical data for the island of Santa Cruz. You see that Puerto Ayora is the town here, which is where Academy Bay, the Charles Darwin Research Station, is located. This is an area where tourists arrive, and as a result, the people in Puerto Ayora have put up bird feeders to attract Darwin's finches so that the tourists can see them. But there are other places on this island where tourists don't really go. One of these is El Garapatero, and one of them is Barrero Bay. And you have long-term data at Puerto Ayora because of the field station, but you don't have long-term data at El Garapatero or Barrero Bay, but El Garapatero acts as a control because there aren't humans there and there are no bird feeders. So what you should be able to do is look at beak size and the distribution of beak size, and you should see the signals of either directional selection or stabilizing selection or disruptive selection. And in this case, what they suspected was in the past, disruptive selection would be happening, which would result in a bimodal peak, a peak of small-beaked finches and a peak of large-beaked finches, just like these finches. And what they found was that in Academy Bay back in the 1960s, there was this bimodal appearance with a mode, a peak of small-beaked finches, a peak of large-beaked finches, and a valley in between where intermediate finches are not very common. That was true in Academy Bay in 1964 and in 1968, but by 1999 to 2002 and in 2003, that valley in the middle had largely been filled by finches. But when you look at 2004 and 2005 data from El Garapatero, you see that there is a typical bimodal distribution, small-beaked finches, large-beaked finches, with a valley in the middle for both of those years. And so something's happening in Academy Bay in recent times that is different from what was in Academy Bay in the 1960s and what is different from El Garapatero in the early 2000s. And this is even more obvious when you plot beak length versus beak depth. And so up at the top here is El Garapatero. You see in the bottom left hand of this figure you have small beaked finches. In the upper right hand corner you have large beaked finches. And there's this gap of finches here in the middle of the distribution. And that same region of the graph at Academy Bay is not found. And this is, of course, taken in 2004. And so at El Garapatero you still have disruptive selection going on, but that disruptive selection has ceased to be a factor at Academy Bay. So at Academy Bay back in the 1960s, you had a population that was undergoing disruptive selection, presumably diverging from one another, the large-beaked finches and the small-beaked finches, presumably the beginning stages of a speciation event, and that speciation event has largely been reversed due to the activities of humans. And so Selection had been driving the two subsets of the population apart. Human activities are reversing that, and so we can now add reversing the effects of disruptive selection to the list of things that reduce biological diversity, along with loss of habitats, climate change, et cetera, all these other things that also contribute to the loss of biological diversity. So that was it. That was all we still had to go through, and that constitutes the end of the semester for new material. Thanks for tuning in.